In this video, I want to discuss with you box plots and empirical rule. If you remember in the past, we talked about histograms, bar graphs, right? These charts, these ways to display data. We talked about mean, median, and mode with these ways to talk about the center of data. What I'll do in this video is to combine those two informations and get some better graphs. Let me dive right in. So again, we talked about the mean, a good way to say, look, this is where most of your data is located, but this is only a small snapshot. It says, hey, look, this one number describes everyone. But that's not often a good description. For instance, I want to know, hey, look, how are my low performers doing? How are my high performers doing? What's their kind of average, the high and low performers? We had quartiles for that, like Q1 for my low performers and Q3 for my higher performers. It was a middle. Those was the 75th percentile for the third quartile and the 25th percentile. So it had good spread for both of those values. And so maybe there's some more numbers that we can kind of put together, maybe like a band, if you will, and they'll have a better picture if we combine them. That better picture is called the 5-number summary. These are a group that we should be able to name the 5-number summary. There are 5 numbers that we're interested in computing. It's the minimum, the first quartile, the median, Q3, and the maximum. Let me index them in this way, and you'll see why later in the video. 0, I'll label this 1, 2, 3, and 4. For the first one, for min, we have a nice Excel function for that. Minimum, we'll do that in a matter of moments. For the quartiles, we had a nice function. It was, see if I can write it in here, quartile.inclusive, where we could fill in an array and also what quartile we're interested in. Of course, maximum had its own function as well. These are very nice 5-number summary, and it gives me a good display, right? I know how my lower performers are doing, first quartile. I know how my top performers are doing, what's their average. I also know the actual maximum and the minimum. I get all these numbers in between. And of course, the median, as we talked about before, is certainly a good substitute for the mean. They had different characteristics. Now what I want to do is I want to take these 5-number summaries and I want a good way to display them, make a great graph with them. This is the combining of a histogram and the mean. You can combine these things and they'll give you this graph here. We'll call it a box plot. Sometimes also referred to as a box and whiskers plot, but box plot is certainly enough for us. Here are the characteristics. So we certainly have the 5-number summary. In fact, I'll list them for you here. We have the minimum, the smallest value. I'll label right here. This is dot over here. If I scroll over to the right a bit, you can see there's the first quartile. We refer to that as the 25th percentile. Here's the median. It's the 50th percentile. And then over here, here's Q3 as the 75th percentile. And then lastly, here's the maximum. So the box plot shows all of the 5-number summary, but it also gives me quite a bit more information. This box, you're like, hey, look, what makes this box special? Well, the reason why we like this box and why we label it as such is this is the middle 50 percentile. We had our 25 and our 75 on opposite ends. So what's in between that? You got it, 50% of my data. And so this is like, hey, look, how are most people performing? Well, 50% of people are within this range, and that gives you a good display of the spread. Let me focus on the right side. If we look at the right side, we'll see the maximum, yes, up top. But you might be asking, what is this vertical line? We label the maximum here as outlier, right? It's an atypical value. But if you remember, we talked about, look, how do I identify outliers? We had a measure for that. If you wanted to identify outliers, you first needed to identify a little line in the sand here, an upper fence, right? It was those fences, the lower fence or the lower fence and the upper fence that identified outliers. And so this box plot, again, you don't write the fences. It's not actually on the graph. But you can see, hey, look, this outlier exists because there's an upper fence blocking it. And so to that end, if I can highlight, this is my largest value. That's a non-outlier. So again, this is not a fence. This vertical line, it might look like a fence, but all it is just the largest non-outlier. It could be the maximum, but if the maximum is an outlier, then it's going to be, hey, look, this is an atypical value. And the box plot will highlight this. One thing I want to mark here, and I encourage you to keep this in mind, is that inside the actual box plot, there are no fences. Or I should say when you actually draw, right? When you actually draw the box plot, you can X this out. There should be no fences visible. Fences are really a bit esoteric. It should be for those people who understand a box plot. They should go, hey, look, how did you know those are outliers? And the people in the know go, oh, I know how those were identified. There are like these invisible fences somewhere outside of that largest non-outlier and outside of that smallest outlier. And so this is the box plot and what it shows. Again, the big characteristics are the 5-number summary. The box holds the middle 50%. And of course, outliers are just outside the fences. We'll do some examples here in a minute. So here we should have a picture of a box plot. Move out of the way a little bit. and you can see those characteristics. These items that are above 1, 2, 3 are just exactly what I talked about previously. You'll see a nice little example over here drawn out for you. This example just demonstrates a box plot for highway gas mileage for various vehicles. And so we can say, okay, look, I know what most gas cars are getting, or maybe what the median is, right? What's the center? I know what the maximum is, the largest value, and I know what the smallest value is. Additionally, I can tell you that although those are maximums and minimums, for here, there are no outliers. There's no atypical, crazy, nobody's breaking the mold terribly. Everything's pretty well ordered. And then, of course, my quartiles exist there as well. Instead of going through this example again, though, let me actually do a more practical example, pulling apart this 5-member summary and the box plot. A local retail chain currently employs 16 managers. The age of the managers are given below. What I want to do is find the 5-number summary. And so the beauty is the 5-number summary is already given to me. All these numbers are listed here. But what I need to do is I need to list what the 5-number summary is and then connect them to the correct measure. First, we'll start off 5-number summary. Again, a great label to put in. The first one is the smallest value I can imagine, minimum. Then I need the first quartile, or the 25th percentile. I then need the median. If you want to be fancy, you can write that as Q2. I then need Q3 for the third quartile. And then lastly, I need the maximum here. So this is the 5-number summary. We have those labels memorized. Now it's time to connect them. Well, minimum should be the smallest value. Either you can look at the table up above, or I can say, hey, look, this 22-year-old is the minimum. Again, this represents somebody's age years old. And this should progress, increase in age as I go up. So the first quartile should be the next smallest number. Here it is, 39. We change colors here to help highlight these. For the median, that should be the next highest, 43. We can connect that one. And one more color change here. For 50, it's the second highest number. That's going to be the third quartile. And lastly, 60 is the maximum. And so again, I don't need to use any fancy technology just yet. That'll come later. I can simply match these once I have them listed. And certainly I can observe, yeah, look, there's my maximum and there's my minimum if we had to do those by hand. But what can we do with this 5-number summary? So one of the big points or purposes of creating that 5-number summary is to identify outliers or atypical, especially you can imagine if we're going to graph, we'll certainly need to identify outliers. So let's say somebody did the work before. Here these are for a reference, Q1, Q3, and the IQR. We'll figure out why we need that in a moment. What I want to do with this example is then find the lower and upper fence and identify any outliers. If there are none, then we'll just simply write none. Let's get into it. Let me start with the lower fence. So I'll write lower fence. There's a formula for this. I'll write it out over here. So equals, I should write this as Q1 minus 1.5 times the IQR. Let me write that in parentheses so it's easier to differentiate. So let's copy these values and then compute. Q1 sitting up there is 39.5 minus 1.5 times the IQR, which is 10.5 computed for us. Now look, I cheated, I did it beforehand, but if you want to try to use a basic calculator to compute it, you certainly can. You should end up with 22.5 if you round. We're rounding to one decimal place here. So 22.5 is what I get for the lower fence. Let me compute the upper fence and then we'll see if we identify any outliers. Upper fence, little formula to compute. Let me copy it down. It should be Q3 plus 1.5 times the IQR. You do these formulas enough, it's just like writing. We remember all of these or we have them memorized. You certainly don't need to. So Q3 plus 1.5 times IQR, it should be for the third quartile, it's 50 plus 1.5 times 10.5, that's the IQR. If you multiply, then add together, you should end up with 66.5. And that'll be our two fences. And so the way I'd encourage you to think about fences, think about them literally being on top of your data. And then if they're outside, then we got issues. My upper fence, 66.5, is sitting out over here. I'll write UF for upper fence. Yeah. Outside here, any outliers? Nah. None to speak of. Uh-oh, here we go. 22.5, we're going to be in a pickle. Because if I draw that lower fence, here it is. I have my first victim, my first atypical value, my first outlier. And so we've identified it as such. And so I should go over here. I should say, again, the question says, identify any outliers? Yeah, we can do that. Draw a little arrow sign. and say, look, we got problem. Outlier, we got one of them, and it's this 22. If we want to give that 22 some units, these are referencing the ages of different managers. And we have one atypical, one outlier. It's that 22-year-old. So let's see if we can take that 5-number summary that we talked about previously, and also this outlier, and actually see if we can create a box plot representing that data. We'll make sure to label each part. Let's try it out. So first thing I want to do is I want to draw a little number line here. All right. And then I want to put my box plot in between here. All right, doesn't have to be beautiful, but it should be at least relatively clean. Again, my components should be Q1 and Q3 over here, with my median somewhere in between. We can look up top. Q1 was 39.5, the median 43. Q3, we can look up top, was 50. So these are my box that contains the middle 50 percentile. Now up top, the maximum, we can certainly actually write the maximum. Here it is, all the way at 60. That was the maximum. You might be tempted to, don't do it though, to write the minimum here as 22. But look, that 22 is not normal. We can't include it here in the minimum. Instead, I need to write a little star here, or you can write a diamond if you want to be fancy, and write 22 because this is an atypical outlier. So I'll mark it here as an outlier. And so this is then going to be the smallest non-outlier. We can look up top at our data. That should be 32. And here we have it, our box plot. One very important thing I want to mention here is, again, in your picture, there should be no fences. The fences do not present themselves in the box plot. I mean, kind of like invisibly they do, right? If I look over here, 22, invisibly they do, but they don't actually show up in the picture. So important to be able to identify. And this is the better graph that I claimed in the beginning, right? Versus seeing everything in a histogram, I can see my data displayed out. This is much more clear as to show the spread, right? I can see where the center is, 43. That's where most of my ages are. But not only that, but I can identify this dang punk over here and say, isn't this strange? Isn't that strange? I have a 22-year-old manager, and it's obvious from the picture that this person is literally atypical. Arithmetic or algebraically speaking, we can actually find and talk about that strangeness. Now, again, maybe there's some nepotism involved. Maybe it's the owner's son. Maybe it's somebody who started when they were 14, right? We're working. And so this is certainly warranted to be identified as strange and something that the graph shows quite readily. Next example. The postmortem interval, or PMI, is defined as the time elapsed in days between death and an autopsy. Knowledge of the PMI is essential to conducting medical research on human cadavers. What a morbid conversation. The data below are the PMIs of 24 human brain specimens. We're going to round our answer to 1 decimal. We're also going to do a little bit of Excel here in just a minute. So we have all of these different time intervals. For instance, this 8.1 means that body sat for 8 days and a little bit longer before it was worked on. I want to compute or figure out what the 5-number summary is, and we can do so with Excel. Let me pull Excel up here. Search Excel. We can pull it up. We can try this again. I'd encourage you to practice along with me. Throw this to the side. Now I want to copy my data first. I can simply select my data here. I can hit Control C. Let me copy it in the same spot, A1, and I'll Control V, paste it in there. So I can see my data listed here. So I want to find this 5-number summary. First, let me give me my labels. It should be min Q2. It should be, or Q1. Silly goose. I want my median, or you can write that as Q2. There we go. Then I want my Q3. And lastly, my max. Now, if you remember at the very beginning, I mentioned that indexing thing, that I want to write this as 0, 1, 2, 3, 4. There's actually a couple different ways I can index this. So this index will serve a purpose, but I want to show you guys something interesting here. Let me say I delete this. Say maybe I'm lazy or I'm typing a bunch of this, 0, 1. What I can do in Excel is I can actually highlight these 2 values. That black cross here, I can click and drag that down. And Excel, if you look over at the corner, 4, 3, right by my cursor, it shows the number that it says, hey, look, I think I know what you want. And it'll automatically type that information in for you or fill it in. And so that's something important that we'll reference here in a minute. So I want to find these values, these 5-number summaries. Like I mentioned in the beginning, there is a function for minimum. It's just equals minimum. But let me show you a cooler, more interesting trick. And it's using this quartile function. Quartile. Remember, we want to use inclusive. Let me hit the tab button to fill that in. Now I want to select the array or my data. That's what I'm interested in. If I go up top, that should be A1 all the way down to L2. That's what my selection here says. Now, one of the difficulties, and we'll get to this in a minute, is I want this to always stay the same. The term we actually use is static. I want it to always remain the same. If you put $signs in front of, that's the column reference A, and $signs in front of the row reference, that'll keep this reference always the same. So again, $signs will keep that static. It will not change. You'll see why that's important in a minute. Let me hit comma. There's my static reference. And then it says this, 0 for minimum, 1 for first, 2 for, these terms should look familiar. That's exactly the 5-number summary. That's what we need to find, except I need to change my input as I progress. Instead of me typing in 0 and then retyping everything again, let me use a cell reference over here. This is E10, and that references the 0. So I'm referencing my data and also E10 as well. Let me copy that over for a reference. And yeah, of course, that gives me my minimum 2.7. So I could go over here and I can type in quartile again, but you were working way too hard. You remember the black cross that we dragged down in the past? We can do the same thing here. Select your quartile reference, find that black crosshair, and you can drag it down. And check this out. For the first quartile, it should keep the same array, a reference now, E11, the next one down. And I can continue dragging this value down. So let me find that black crosshair, drag it down, and it'll give me the median, Q3, and the maximum. So that's why we have that static reference, double click, why we have that static reference for the array. And that way, as I drag down, it doesn't also, you can imagine pulling down my data reference. Then we would not get the correct answer here. So that's why the indexing is friendly. But there they are, 2.7, 5.05. One issue that we're running into, and you can see this if we look over to the left. Let me bold these answers. So one issue that you can run into is if we see, look at these answers, this says round to 1 decimal place. I want to show you a trick. Certainly 2.7 is done. You don't need to worry about rounding that one. But this 5.05, we should worry about it a little bit. If we look up top on the ribbon, this home ribbon, if you click that, we should be able to drop down and it says, look, number. This represents how it wants to present your data. Excel automatically is like, hey, look, I think you're referencing a number, and yeah, we are. So click that drop down, and we should see a little arrow keys over here. This will actually automatically round numbers for you. A nice little pro tip for you. Again, that's home, go to numbers, and you can hit the arrows to give it either more decimals or fewer. If you want to give 1 decimal, well, you have it. There you go, 1 decimal to speak of. Now look, I only have the 1 cell selected, so it's only doing this for the 1. How silly. What I can do instead is I can highlight all of my answers and go to home, numbers, and I can look at the decimal places and I can say, look, I want all of you, that's 0 decimals. And no, I want everybody to give me 1 decimal. And then you can click off or you can enter, and voila, everything's automatically rounded for us. Again, no looking at individual pieces. Hey, which one? 3 decimals, 4 decimal places. We can get done automatically. Let me fill in at least one of these for our reference. So there's our referencing for pulling these information in. And make sure you got that cell, and then also what quartile you're interested in putting. 0 for the minimum, 1 for the first quartile. And we can get, there they are. This is all the 5-number summary. So what can we do with that? They computed the lower fence and they computed the upper fence. What I want to do is I have 4 different box plots below to choose from which one follows from the data in the 5-number summary that we computed before. The first thing I'd encourage you to do whenever you see fences is to say, look, can I put this on my data? Can I identify any outliers? That usually will get us the answer we're interested in. So let me draw my little line over here. That's for the lower fence. And nothing caught on that side here for my outliers. If I go on the right side though, 10.9, ooh, here it is, look at this. Upper fence, we have a couple. Ding, ding, right here. Outliers indeed. There they are, 11 and 14.5, which means on my box plot, those should be outside, little stars or diamonds somehow outside of the quote unquote normal data. So as I go through my list over here, as I go through my list for that first data set, again, this is saying that 22 is an outlier. I look at my data. No, that's not even my right data. So that one certainly can't be it. Over here, it certainly matches my Q1, my median, my Q3, but this one has no outliers. But from the fences, I've identified outliers. So that one certainly cannot be correct. Let me look at, over here. Let me look at my 4th data value. Okay, this one identifies 2.7 as an outlier. But as we just discussed, it's not an outlier. It is very normal value, very typical. Okay, well, this will lead us to our last option over here, 2.7 minimum, non-outlier, 5.1 first quartile, median Q3, 10.7 is, if we look up top, the smallest or the largest non-outlier. And then here we are, outlier, atypical. Yeah, we're for sure good. This one is the correct box plot already drawn for us. And so these are ways that we can identify, again, a better graph. Instead of looking at a histogram where we're saying, okay, look, all the bars are relatively the same, I can get a snapshot, a bunch of different values, a picture that shows me really quickly, I can identify outliers and say, look, these two human cadavers, these were the period between them being autopsied was way too long. And so maybe if I pull data from that, maybe we're measuring certain synapses or degradation of cells. These two may not be beneficial because they are way aged beyond the norm, versus we can identify what we can expect, what the median is, what most of these cadavers lay about. Again, I apologize for the morbid example. Let's continue. We talked about better graphs. Box plots is certainly an excellent best graph, but I want to introduce to you one graph that we will use. I mean, this thing is all over the place. In fact, it has a lot of different applications. This is only our first introduction into it. It relates to z-score. Remember, z-score is really beneficial for understanding position. If I look at this nice, we call it bell-shaped curve, here's my most observations. It's representing the mean, center, the mean, mu. That's the highest point on my graph. What I want to do is a 17.23. If I use the z-score formula, I'll end up with a z-value, z equal to -2. Now, a quick recap, if you will. On my little chart, let me see if I can zoom in here. On my little chart, that's a little better. On my little chart, we can see the mean sitting over here, and -2 represents that actual value. And so up above, I could write that 17.32 value to say, look, this is the line in the sand. And just like we talked about before, that means I'm below the mean. I can see I'm an underperformer if I just look at -2. In fact, I can tell by how much I'm a lower performer. But here's the application. If you have roughly bell-shaped data, again, that's what this is. You can imagine holding the tippy top of it and ring, ring, ring. Yes, okay, kind of looks like a bell-shaped distribution. Then we're going to have certain proportions. These are very fancy numbers. They show up a bunch. 68%, 95%, 99.7%. And this percentage of data, remember we talked about the middle 50% for box plots? These are middle proportions or middle percentages that are going to fall within certain ranges. In this case, it's going to be the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard deviations, and the mean plus or minus 3 standard deviations, respectively. So if I let me draw an arrow up over here for my mean plus or minus 2 standard deviations, which according to this roughly bell-shaped should contain 95% of my data. The mean plus or minus 2 standard deviation refers to, this is minus 2 standard deviations. All the way on the right, this is plus 2 standard deviations. And if I was to say, look, how much data did I include in here? Well, I know, roughly speaking, it should be 95%. Again, much like our box plot example we talked about in the past, where I have my Q1 and Q3, where this is going to contain my middle 50% of my data. That's a lot like what we're talking about here. But instead of just having a number line where I have these nice mile markers, well, now I have almost like a combination between a histogram. It's really what this looks like. This is called a frequency distribution. It looks like a histogram. And a box plot. I can have these ranges where I know how much data is going to be contained within certain intervals. And that's what we're going to look at an example. If I move over here, we can see all these different pictures or these different distributions for, we call it this bell shape, for different means and different standard deviations. So if I focus on this blue graph going up, again, it's bell-shaped. You can imagine grabbing it and ringing it. It has a mean, M for mean, I know it's confusing, of 900 and a standard deviation, SD, of 120. And that's the shape of the graph we'll take. Compare that distribution, again, standard deviation of 120. Compare that with this much taller graph. Holy moly. That means that all of my data is squished closer together. Why would it be squished closer together? Well, look at my standard deviation. For the yellow, the standard deviation is 50. That's quite a bit smaller. And so my data is more close together. Certainly you can imagine the red. Look at that huge standard deviation, 220. I mean, this data is just flattened out. It's all over the place. It's hard to pinpoint exactly where the data would lie. And so again, this bell shape is a very common distribution, and there are a lot of applications therein, but we should understand the mean is the middle and the standard deviation is the spread, how wild, how moved apart your data is going to be. But all these will follow plus or minus 1, plus or minus 2, and plus or minus 3 standard deviations. Let me show you. So this rule is actually a very special one. Move out of the way over here. Very special rule. This is a nice term that we'll use, much like box plot. So this one we'll use really throughout the course, and so I'd encourage you to hold on to this one. And it's the empirical rule. It says this, that if you have plus or minus 1 standard deviation, again, this is for sample. So these represents z-scores. Z is equal to -1 to +1, meaning the mean minus a standard deviation, the mean plus a standard deviation. This is an interval that is going to contain 0.68 of your data, or 68% of your data. If I expand that out one more into 2 standard deviations, there's -2, there's +2. Here's my z-score. It's going to contain 95% of my data. And then, of course, the last one, you can see, well, if I get out of the way, you can. This is what's going to be given to you, or that you can use on a formula sheet. It's going to say, hey, look, let me zoom in so we can actually see what we're dealing with here. Boop, there we go. So we have this empirical rule. It says this, look, the mean smack dab in the middle. And if I subtract 1 standard deviation, that's the mean minus standard deviation. And the mean plus standard deviation, that's going to contain 34 plus 34. That gives me my 68% of my data. And so this is much like we had the box plot before, where I said 50% or 25% in between these quartiles. Well, now we have a much more intricate breakdown, but this data should be nicely shaped. Again, should be bell-shaped. Let's see how we can use the empirical rule with various examples. Good. A big question that often shows up is if we have a big string of data, for instance, this large group here, I want to know, is this data roughly bell-shaped? Is it a nice distribution? That's what this example explores. Let's say 30 students in an experimental psychology class use various techniques to train their rat to move through a maze. Below are the results in minutes of the rat's time to complete the maze. Use the data and listed information to determine the actual percentage of measurements in the intervals, the mean plus or minus 1 standard deviation, 2 standard deviations, and 3. And the big question that we'll hope to answer is this data roughly bell-shaped? Let's see. So they're giving us the mean. So this X bar that's the mean. And they're also giving us the standard deviation. They saved us some time. What I want to do is compute these intervals. What is the values that make up the interval, the mean minus 1 standard deviation, the mean plus? These are 2 different values. I'll write a 1 under here and a 2 underneath here. So for the first one, I have X bar minus the standard deviation. I can compute this. This should be 3.7 minus 2.2. If we subtract these two, pretty finely enough, it should be 1.5 for my first endpoint. For the second one, it was the mean plus a standard deviation. That's going to be 3.7 plus 2.2, and that's going to end up being 5.9. And so the interval, the values that make up 1 standard deviation plus or minus is 1.5, is 1.5 all the way to 5.9. This is the interval that makes up 1 standard deviation plus or minus. All right, what if we expand that out to now 2 standard deviations? We can compute this. In fact, the calculation looks quite similar. That I should write this as X bar minus 2 standard deviations. And here's my first calculation. That's going to be 3.7 minus 2 times my standard deviation was 2.2. I cheated, did it beforehand. You should end up with negative 0.7 for my smaller, my left endpoint. For the second one, the larger, it should be X bar plus 2 standard deviations. That should be equal to 3.7 plus 2 times the standard deviation of 2.2. Again, I cheated, did it beforehand. That should be 8.1. These are my 2 endpoints that make up that interval. So if I put this together, I should end up with negative 0.7 all the way to 8.1. And these are my 2 endpoints. Again, you can think about these like I'm trying to capture as much data as I can between these 2 endpoints, almost like fences that we've talked about. in the past. So with those fences in mind, let's see if we can look at what percentage of data lies within these different ranges. Again, here we are 1.5 to 5.9. And so I can look and again, treat these just like we would fences. On the low end, I have 1.5, it should be right about here. There's my low end. And on my high end, I should have 5.9. Looks like that cuts off right about here. So I can simply count these data values. It should be one.
Bum, 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 bum.
So my count was 23. Now I want to find a percentage, or you can think of a percentage as a relative frequency. If I want a relative frequency, that's simply the count or the frequency divided by the total. And so to find the actual percentage that we're interested in, I can simply take my frequency, 23, and divide it by the total. And they said up here 30 students did this test, so I should have 30 pieces of data. If you divide that, you should get 0.767. The decimal actually repeats, but we'll leave it alone at that. If I want to write this as a percentage, I can do that. Let me move this decimal place over 1, 2, and you should end up with 76.7%. We'll talk about what that percentage means in a moment. If I expand that gap to no longer be 1 standard deviation, but now to be 2, that's what this next one is, from negative 0.7 all the way to 8.1. Look, let's not reinvent the wheel. Let me simply add on those additional values. I had 23 to start with. How many am I going to improve upon? Well, I'm going to get these other 3, 1, 2, 3. So plus 3 on the low end, plus what about on the high end here? I'm going to have all the way to 8.1. That'll be 1, 2. So I get 2 more on the high end. So altogether, my total count is 23 plus 3, 26, and then 28. So if I want to find the percentage, I can do so. That should be now 28 divided by 30. If we do the calculation there, and again, put it back into percentile, or into percent, I should get 93.3%. Yep, we can box that. These are the percentages of my data captured inside of these ranges. So here's the application. So if I look at my percentages that I captured, we move out of the way of this little chart that we're going to use. The big question is, does the data seem roughly bell-shaped? All right, I'm covering the graph. We'll talk about that in a minute. But the big question that we can look at is exactly these standard empirical rules. Again, the empirical rules only works for bell-shaped distributions. Well, we just did our calculations. The first one said 76.7%. Big check mark. That one's perfect for the empirical rule, no problem. 93.3%, a little bit wavy, but yeah, it's close. 95%, 93, yeah, it's pretty close. And so we'll give a half-hearted check mark there as well. I'm sure if we went out to 3 standard deviations, we'd actually find that 100% it captures all of my data. And so this certainly is looking like it roughly fits this empirical rule. And so certainly go in that regard. Additional help for our interpretation here is to look at this histogram. Let me zoom in on it for us. This histogram is of our data. This is the runtime for those mice, and a histogram built out. Again, we had a lot of people around 2 minutes, 4 minutes. This is our high points. And I superimposed an empirical rule in there. Certainly not perfect, but we can see, yeah, most of our data is trapped around the same point where, again, it's not perfect, but it does kind of follow a normal distribution. Oftentimes we call this data semi-bimodal because there's kind of 2 peak points, but certainly I can imagine this kind of shrinking around one normal distribution. So certainly it looks like it may fit roughly bell-shaped. Additionally, again, this one's like kind of, we can speak properly, kind of bell-shaped, and certainly mostly fits those rules. I would say this data, although not perfect, not beautiful, certainly is roughly bell-shaped, which in the study world is absolute. Much of data needs to be normally distributed in order to even talk about applications. That's one application of this empirical rule, is looking at data, figuring out if it roughly fits these rules. We can also look at other standards, is a big point of empirical rule, and it relates to the z-score that we've talked about in the past. Let me show you an example. The distribution of weights of newborn babies in one region is bell-shaped, it's an important word, with a mean of 3,000 grams. and a standard deviation of 500 grams. Note that 1 pound is roughly 500 or 453 grams. And so that'll give you a good scale for how much these babies are weighing in this one region. What I want to do is I want to use the empirical rule to determine the two weights which contain the middle 68%. Remember I said there were those three percentages that are going to come up quite often? 68 was one of them, 95 was another one, and then 99.7 was another percentage. These ones show up often. I encourage you to have in your back pocket. 68%, here's a little chart, refers to these ones. Again, the mean, sitting right over here, this is the mean, is the middle. And so if I want the middle 68%, well, then I want these two values. I want those values pulled. And so this question, use the empirical rule. Okay, we should use that on a chart to figure out the weights that contain the middle 68. It's these two values. If I was to draw a line in the sand here, for the mean minus 1 standard deviation, and another line here, the mean plus 1 standard deviation, that does contain the middle 68% of my data. So really this question can be translated into the mean, the mean minus 1 standard deviation, and figure out what the mean plus 1 standard deviation, because it's these two values that will contain the middle 68. For the first one, the mean is simply 3,000. So I'll write 3,000 minus 1 standard deviation should be 500. No problem. It should be 2,500. That's going to be the first weight, the smaller one. On the larger end, adding 1 standard deviation, that's going to be 3,000 plus 500. That's going to be 3,500, and that's my larger value, 3,500. Now, both of these measures are in grams, and so if you want to put those into pounds, I did that for us down here. That represents that, look, if you want to know where are most babies inside of 68%, well, they're moms, but for their weights, it should be 5.5 pounds all the way to 7.7 pounds. And so if, again, you're nervous or the doctor's talking, you can know, okay, look, even though it might be on the low end, 5.5, it's actually very normal. Middle 68% of the data is contained in those two ranges. So that's what most people will experience. What else? Let's see if we can do it in reverse. Let me show you what I mean here. Use the empirical rule. What percentage of newborn babies weigh between 2,000 grams and 4,000 grams? What percentage? What percentage? We had our standard rates before, that 68, 95, and 99. If you want to take a guess, you're welcome to guess which one of those three, but let me show you how to figure out exactly it. If you remember, we have our nice little chart here where I actually know what the mean is. The mean is 3,000. I know what the mean minus 1 standard deviation is. We just computed it. It was the 2,500. Well, you know what? I'm going to do my pen out for this one. If I write here, this was 3,000, and then over here, this was 2,500. If I subtract another 500, so again, if I do the mean minus 2 standard deviations, that'll actually equal, for us, 3,000 minus 2 times 500, which will be, this number is familiar, 2,000. That's what this number, the mean minus 2 standard deviation, is representing, 2,000. And we can clean that up. 2,000. And so this is that first endpoint that they're speaking of. Again, 2,000 to 4,000. That was the first one. All right, maybe we can figure out the game here. If I keep going to the left, though, I'll keep subtracting 500. That's the wrong direction. Let me move over in the right direction. Over here, this is the mean plus 1 standard deviation. That's 3,500. Again, I could just keep adding 500 as I move along for the standard deviations. That means the mean plus 2 standard deviations is going to be 4,000. Oh, there we go. Look at that. We just figured it out. This is my other endpoint. This is in between 2,000 to 4,000. So if I actually want to add this up, I can figure out what values are between 2,000 and 4,000 by simply adding up these percentages. This is what percentages are contained within this interval. It looks like 13.5% plus 34% plus 34% plus 13.5%. If you add that up, you can, or you can simply know that, look, the mean plus or minus 2 standard deviations is going to contain 95% of your data. Let me move out of the way. There we go. And we have it there. These standard ratios. If we wanted to be a bit trickier, we could certainly change this to 3,000, and then maybe the math will look a little different, but certainly you can imagine the work would look very similar to the example we did. Z-scores, empirical rule, can often be used to set standards, to say, hey, look, we want top performers. This example exemplifies that concept. A professional F1 Formula One driver must have a reaction time faster than a Z-score of -3 standard deviations below the mean reaction time of motorists. The mean reaction time for the general population is 900 milliseconds. It's a pretty quick reaction time. And a standard deviation of 200. What we're curious of is, what is the slowest reaction time of an F1 Formula driver? You actually don't need the chart here. I wanted to throw us off a bit. If I look, it says the actual slowest reaction time. This refers to what is the Z-score. Again, this Z-score, Z equals -3, is the reaction time. That Z-score doesn't actually tell me what milliseconds. And so what I need to do is find out what the X value that relates what is the Z-score. For your reference, the formula for Z-score is Z is equal to X minus the mean divided by the standard deviation. And so let me plug in the values that we do know. I know -3 for the Z-score. I also know, oh, not the X value. That's okay. I'll just write X in there for short. Minus the mean, 900, divided by the standard deviation. That should be 200. We have a little algebra to clean this up a bit. Let me multiply that 200 over to the left-hand side. And you should get, if you multiply that over, we'll get -600 is equal to X minus 900. I then need to add that 900 over, and then I should be left with a little arrow sign so close. We'll get 300 is equal to X. As I'll write it up in the answer spot, that should be X is equal to 300 milliseconds. And this is the reaction time. Again, oftentimes these Z-scores come, you can think about them in pairs, but Z and X. It's just different perspective on the exact same item. -3 is the exact same observation that 300 is. Wow, what a fast time. 300 milliseconds compared to the average 900 milliseconds. That's quite a bit faster. But how likely is it to bump into somebody, let's see, that has this reaction time? What is the proportion of people from the general population which have the reaction time less than that of an F1 Formula driver? Hint, use the empirical rule. Let me show you how we're going to do this. So the Z-score is actually the more friendly term that we want to use. Here we go. All right, Z is equal to -3. If I look at our empirical rule, again, it's a bit hidden in there. This is the mean, 1 standard deviation, 2 standard deviations. If you remember, Z-score measures how far away an observation is from the mean. We're -3 away. It doesn't mean that we're -3 units, though. It means we're -3 standard deviations. And so this observation, this -3, actually is the same thing. I don't know if I can write it down here. Is all the way over here at -3. This is, that line in the sand, is this -3 Z-score, because it's the mean -3 standard deviations. And so to that end, I want to know what probability is less than that. That's smaller than my Z-score of -3. So it's just going to be, if I can zoom in again, just going to be that portion, in the tail end there, which we can barely make out. That's not 15%. That's 0.15%. Oof, if you're hoping on it, I would not count on it. All right, left of the mean -3 standard deviations. And it looks like the only percentage there is 0.15%. Again, don't count on it. By the way, here is 0.15%. If you want to write that as a decimal, that would be 0.0015. I wouldn't count on it. That is considerably unlikely that we would have these, that we bump in these individuals. So this section, let me wrap with this. This section talks about these better graphs. Again, we talked about histograms, we talked about bar graphs, pie charts. Those are great. We talked about mean, standard deviation, these different measures. But when we start to put these numbers together, it's what statisticians like you and me, we can tell a lot more information about, hey, look, how likely is it, or what's the proportion of people that have this certain characteristic, that have the Z-score? Or better yet, when we talk about box plots, we can look at where are most of my people located. It's much more information instead of just this one single value that's supposed to represent everybody. These better graphs that give more information. Look, if you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.